Welcome to Cambridge IGCSE Physics, Lesson 28.1, Refraction Basics. Today we explore how light changes direction when passing between different materials. This fundamental concept explains many optical phenomena we observe daily. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, define and use key terms: normal, angle of incidence, and angle of refraction. Second, describe experiments showing refraction using proper scientific language. Third, use transparent blocks of different shapes to investigate refraction. These objectives align with Assessment Objective 1, which focuses on scientific knowledge and understanding. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, refraction means the bending of light when it passes from one material to another. Second, normal is an imaginary line drawn perpendicular to the surface at the point where light hits. Third, angle of incidence is the angle between the incoming light ray and the normal line. Understanding these terms precisely is crucial for describing refraction accurately. Let's explore our first core concept. What is refraction? The fundamental principle states that light changes direction when entering different materials. This happens because light travels at different speeds in different substances. The definition is, refraction is the bending of light rays when they pass from one transparent material to another. Key points to remember: light travels at different speeds in different materials. This speed change causes the direction change, and refraction only occurs at the boundaries between materials. The diagram illustrates a light ray passing from air into glass. Notice how the incident ray bends toward the normal when entering the denser material. Now we examine the experimental method for investigating refraction. This follows Cambridge IGCSE standards. The apparatus needed includes a ray box to produce a narrow beam of light, a rectangular glass block, white paper for recording, a protractor for measuring angles, and a pencil for marking. The method consists of these steps. First, place the glass block on paper and draw its outline. Second, shine a light ray at an angle toward one face. Third, mark the path of light entering and leaving the block. Fourth, measure angles using a protractor. Safety is important. Avoid looking directly at the bright light source, as this can damage your eyes. The diagram shows the complete setup with light bending as it enters and exits the glass block. Let's work through our first example about measuring angles correctly. The problem states, a light ray hits a glass surface. The incident ray makes 30 degrees with the normal, and the refracted ray makes 20 degrees with the normal. We need to identify these angles correctly. Step 1. Identify the incident ray. This is the ray approaching the surface from air. Step 2. The angle of incidence is 30 degrees measured from the normal line. Step 3. Identify the refracted ray. This is the ray inside the glass after bending. Step 4. The angle of refraction is 20 degrees measured from the normal. Remember, all angles in refraction are always measured from the normal line, never from the surface itself. Example 2 applies pattern analysis to refraction data. The problem is, analyze refraction measurements for an air glass boundary to identify patterns. The data shows paired measurements of incident and refracted angles. Now we analyze systematically. First, plot the angle data points on a graph. Second, identify the pattern trend. Notice how the points form a smooth curve. Third, compare incident versus refracted angles. The refracted angle is always smaller. Fourth, draw a scientific conclusion. Light bends toward the normal when entering a denser material. The graph shows this relationship clearly, with refracted angles consistently smaller than incident angles. Essential skills are crucial for successful refraction investigations. Let's examine 3 key techniques. First, angle measurement using a protractor. Place the protractor center exactly on the point where light hits the surface. Align the baseline with the normal line, not the surface. Read the scale carefully, choosing the correct direction from 0 degrees. Second, ray diagram drawing requires precision. Draw all light rays as straight lines using a ruler. Show arrowheads clearly to indicate the direction of light travel. Third, data recording must match your instrument precision. Record angles to the nearest degree, as this matches typical protractor accuracy. Take multiple readings and calculate averages to improve measurement reliability. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks you to define refraction and state when it occurs. Use the scientific definition we learned. Question 2 is intermediate level. Light enters glass at 45 degrees to the normal, and the refracted ray is at 28 degrees. Which angle is larger, and explain why this happens? Question 3 is advanced. Describe how to investigate refraction using a glass block, including all safety precautions. This tests your practical skills. For all questions, remember to use scientific terminology, show clear reasoning, and check your answers make physical sense. Refraction principles power many modern technologies. Let's see how today's concepts apply in practice. In optical lenses, cameras focus light to create sharp images, microscopes magnify tiny objects, and telescopes gather light from distant stars, all using controlled refraction. In fiber optic cables, light signals carry internet data around the world by staying trapped inside glass fibers through total internal refraction. In eyeglasses, specially shaped lenses bend light to correct vision problems like nearsightedness and farsightedness. These applications create exciting career opportunities in optical engineering, telecommunications, and medical technology. The refraction concepts you learn today become the foundation for designing camera lenses, performing laser eye surgery, and developing faster internet communications. Let's review the solutions to build confidence. For question 1, refraction is the bending of light when passing between different transparent materials. It occurs at the boundaries between materials with different optical properties. For question 2, the incident angle of 45 degrees is larger than the refracted angle of 28 degrees. This happens because light bends towards the normal when entering a denser material like glass. For question 3, the method uses a ray box, glass block, and paper. Draw the block outline, shine a ray at an angle, mark the light path, and measure angles with a protractor. Safety requires avoiding direct exposure to bright light. For exam success, define terms using precise scientific language, draw clear diagrams with labels and arrows, always measure angles from the normal line, and state observations by describing exactly what you see. Let's summarize today's essential learning points. First, refraction occurs when light bends while changing materials because light travels at different speeds in different substances. This speed change causes the direction change we observe. Second, angles in refraction are always measured from the normal line, the imaginary line perpendicular to the surface, never from the surface itself. Third, systematic investigation uses a ray box and glass block following proper experimental procedures. For further study, practice measuring angles accurately with a protractor, develop skill in drawing precise ray diagrams with rulers and arrows, and prepare for our next lesson on Snell's law, which provides the mathematical relationship governing refraction. Today's foundation concepts are essential for understanding more advanced optical principles.